Thank you very much. In essence, what I'm going to talk about here is one of the results that we came up with in an EU project in the Antidote DB. And I'm going to introduce you to the ideas, to the motivation that we had when we started building this database. So, what's the motivation? Let's assume that you want to build a highly available distributed application. What does this mean? Well, in essence, you want to make sure that users, wherever they are located on Earth, experience short access time to their data. So what you want to do, for example, if you have in a global company, you have, for example, a calendar app that is shared, that shares calendars between the employees. You have employees in America, in Europe, in Asia. What you want to make sure is wherever they are positioned, they access their data with low latency. The application should be highly available, so as little downtime as possible. And if you ever worked with group communication software, a particular problem that at least we are running into very often is when you have concurrent modifications. It can happen that users try to modify the same application, the same appointment at the same time. I'm modifying the people who are attending, another person is modifying the room where things are happening, and what you get is an arbitrary result. Yeah? Changes are lost, people are not notified when these things happen, and this is very bad. So we have, even locally in our research group with like 10 people, we very often have this problem. Now if you scale this to a global company, it gets really, really worse. So if these are your requirements, you need to build such an application. What are you going to do? Well, you probably need to have some form of storage. So what you're going to do is you're going to replicate your storage. Each of the different locations here get their own replica, their own instance of the data store, such that when people access their data, they just go to the closest locally available data replica and just grab the data from there. The problem there is the combination of data loss and high availability is going to give you trouble there. High availability usually means that you want to be able to grab your data all the time, but depending on where you're hosting it, it can very easily be that your data gets unavailable. Also, if you think about certain countries, there is actually maybe even a person who is able to pull a plug and makes your data not reachable for some time. So how do you deal with the situation? You have to accommodate for this somehow. In theory, there is, the theoretical people have worked on analyzing the situation and came up with something called CAP theorem. So the C stands for consistency, A for availability, and P for partition tolerance. So partition tolerance is a situation that when the network is kind of broken, you still want the application, you still want the data, the application to be working, you still want the data to be available. Now, as I said, partition tolerance is kind of something that you inherently want to do. There is very seldom, unless you're kind of Google or so and have a lot of money, you don't really have a way of circumventing the problem that the data is going to break down. So what you kind of need to make sure, what theory kind of says, it's not possible to have partition tolerance, consistency, and availability at the same time. Yeah? If you really need to have partition tolerance, this means you're going to trade something of the other two. So you're going to either reduce your consistency properties or you're going to reduce your availability in some way. Now, some people are happy. Some people value consistency a lot, so they don't want people to see diverging state. So what you're going to guarantee is across all replicas, wherever you are accessing your data, you will get exactly the same result. This makes developing applications on top of such a consistent data store much simpler, because you only have to deal with one situation. There's always the same data. The problem is that latency can be pretty high, because before a replica is going to give you an answer for your request, it kind of needs to check with all the other replicas what's actually the state. So you're going to pay some price for this synchronization between the replicas. And as I said, in time. So under partition, you will be consistent, but you might not be able to give an answer, so you're going to lose availability. This is not acceptable for many people in many situations. So there's also a kind of group in group of developers who are rather going to trade consistency in order to obtain availability. So what you get in this situation is that state, so the different replica state, might diverge, at least for a short amount of time, hopefully. But it can be, if you ask one replica for the data, you will get one version. If you ask another replica for the data, you might get completely a different answer. So the state divergence is an issue that you have to deal with often, even on application level. What you kind of gain is you have low latency. You can replicate your data more easily while keeping availability. However, you kind of have weaker guarantees. So if several people are modifying the same data item at the same time, what should happen, right? So you don't get the kind of guarantee that says it's exactly going to be this and this value. Yeah? So there's some weakening in the guarantees that the data store is going to provide. And this means that if you're building your application on top of this, you have to think hard. So there's real challenge for building the applications. And over time, several different notions of this trade-off between consistency and availability have been discussed. And if you look into the literature, into research, a lot of different notions have popped up. So something you're probably familiar is this keyword eventual consistency. This is at the very end here of the available under partition part, whereas notions like strong serializability would fall under the consistent under partition part, but there's a spectrum here. The only problem is there is kind of one line that divides between this I can be consistent to a certain degree under partition and I will be available under partition thing. And we're going to see where this line is actually lying. Now, if you look into what the market did, so what industry came up regarding this tension between availability and consistency, you will see there is, if you look into the database market, there's a huge variety of data stores. Yeah? Some of them I would classify as AP-oriented, so DynamoDB, Cassandra, React, they fall all in the group of saying, I want to be available under partition. I'm going to deal with the consistency somehow. So if you very clearly or very deeply look into the documentation and so on, it's not in all situations clear what will be results of requests that you're sending to the database. Another problem that you have is programmers are typically trained to use something like SQL and transactions in order to group operations for communicating with the database. For these data stores, you typically don't have transactional support. So they offer, in general, a very low-level key-value interface where you can kind of retrieve a value that is stored under a key, and you can put it in. Yeah? If you want to retrieve several values and put several values, you usually don't get any guarantees in which order these things are happening, when they might be visible on other replicas, also that they get visible together or something like this. This is usually not given, but you are available, so your application is running all the time. On the CP part, for classical SQL stores, you usually have some form of, if you look at Oracle product or so, you have some form of specifying what the semantics, the consistency semantics should be. And you there can get strongly consistent semantics for your data store. More recently, some more cloud databases have also emerged that provide you with strong consistency guarantees. The Google Cloud Platform and also Cosmos DB from Microsoft, they saw that the struggle of programmers to writing the applications on Cassandra, on React, and so on. So what they came up with is they are going to give you much better guarantees. You get strong consistency guarantees. You get support for transactions, also for queries. However, you need to host your data on their data stores. The reason is, well, they invest quite a lot into infrastructure in order to give you these guarantees. But this might not be the way for you to go in all situations. And what you will pay with anyway is comparatively high latency. There will be some coordination across sites happening at some point, and this might lead to a small but still penalty that you will have to pay in this problem. So I personally, I'm falling into the AP category. So what I actually, if I write my applications, the areas that I'm looking at, I want to really have availability. Customers are very, very unhappy if they open their application and you kind of get I cannot do anything because there's some network issue thing. So you're really blocking people, and this is very expensive for companies for sure. So if you if you put yourself into the AP group and availability is kind of the goal that you want to optimize for, then there's one more thing that you have to keep in mind there. So regarding the divergence, it's maybe not so, it's unavoidable that data diverges if there are concurrent modifications. So you have to deal somehow with this divergence and how you can react to it. One thing to consider here is updates take time to travel to another location, at least the speed of light. You cannot beat the speed of light on Earth, right? So if you are not going to, if you don't want to wait for updates to arrive from other replicas, then what you have to do is you have to look at your local data. So what do you have at your local replica? If you connect to it, what kind of answer can you give? Kind of immediately without coordinating with other sites. And we want to do this both for reads and for writes. So what we will do is we are going to modify our data on the local replica immediately, such that the local replica gets the updates directly. All the other replicas are notified about the updates eventually once they kind of trickle in from the other sites. And what we then want to ensure, like on database level, not on application level, on database level, is that at some point eventually we can recover the consistency. So as soon as, if I have two replicas, as soon as they have seen the same set of updates, the same amount of updates, they should actually agree on the same state of things at some point. So if you look into the market, as I said, it's a bit difficult at the moment. So you can get these databases with strong consistency. You can get these databases with very low consistency. But what's kind of in between if you don't want to go for the one extreme or for the other extreme? So what we came up with is a database called Antidote DB. What you get there is a cloud scalable database. You can place replicas on different geo-replications. You get high performance. So we will usually shard data, so put them into different parts and make sure that the synchronization and so on happens to these different parts. You can access the data also in parallel if you contact a single replica. So we have parallelism across geo-replicated sites. We have parallelism within a data center. Support transactions, but not the strongly consistent transactions you might expect. A weaker form that I'm going to explain in a moment that gives you atomic updates and consistent snapshots to work on. This data store is written in a functional language, so that's, from my point of view, the good thing. For this audience, it's unfortunately not Haskell. We could not find enough Haskell programmers to program that, so we had to move to another good choice. So for us, Erlang was a perfect solution because it allows us to use the actor model that Erlang is providing in a very, very nice way. But we have client drivers for different languages. So currently developing also a client driver for Haskell, which in the current state kind of looks like something like that. So what we have here is we are going to run one transaction that consists of several read and update operations. So we have here an update operation, here a read operation. These operations here work on objects. An object that we have here is, in essence, an object identifier consisting of a bucket name. If you want to place objects into different buckets for namespace reasons, say, the key of the object within that bucket, and we have here different types. So what we are going to discuss later is what kind of data model we have with Antidote. It's in essence, it's a store where you can work on typed objects. So we have, for example, counters, we have sets here, and you can add, you can update these objects here by, for example, incrementing counters, by adding elements to a set, by removing elements to a set. If you want to see the current state of the object, you can do this read operation that would give you, in essence, the informations up to a certain point that are available at a replica that you're going to contact. So what you have here is a context in which you're going to run a transaction. A transaction is in essence just a combination of these updates and reads. The updates get visible to other clients only once the transaction is finished. So upon return of this monadic action here, run the transactions in a specific context that kind of tells us what we have seen so far. I'm going to explain this in a second in more detail. And another convenience that we added to the Haskell library for the moment is that you can use a connection pool to the database. So you specify kind of how you want to connect to it, on which port, which host, how many connections you want to keep open in a connection pool at the moment, and within this context, it then chooses one of the available connections and is going to run the transaction on the on this replica that is hosted at this location, in essence. So the data model, as I said, typically with key value stores, what you in essence have is you have a key and a value. What a value is does not matter really to the data store. So for example, if you have a replicated integer in a classical key value store, you could store it under key x, say, and you can set a value. For example, if this is an integer, you set a value to 1. At another replica, you could here set a value to x. So all these 3 lines here correspond to different clients executing operations on different replicas. So each of this line here is a replica of the data store. If you execute your operation here, say on the third replica, it will immediately apply the operations here and then propagate the operations to the other replicas. Now, what happens is, non-surprisingly, these operations happen concurrently. So this is happening at this one replica, this at the other replica at the same time. And what now unavoidably will happen is that the update here is done first. Then this update setting x to 3 is done here second. So if I really apply the updates in this order, the value here should probably be 3 for that first replica. Now in the replica down here, I first set x to 3. Later, the update of setting x to 1 is transmitted to the third replica. So this would have value 1. Now, is this really what we want? One replica ending up with value 3, the other ending up with value 1? Not really, right? Because this would require us to manually or on application level find out about these conflicting updates and do something about this. So what we want to have actually is a kind of decentralized conflict resolution where we make sure that by design this situation cannot happen. So we cannot end up in a state where the replicas diverge. And we want to make sure that we don't need any user interaction because this is just asking for trouble. So what we have to consider is how are we going to propagate updates? What information are we going to propagate there? And what we will see is there are some policies in order to get such a conflict resolution that are generic, so that would work for any kind of data, and some policies that we can apply to specific types of data where the semantics of the concurrent update depends on the underlying abstract data type. So let's look at a very well-known, in practice, often applied generic policy. It's often called last writer wins, so LWLW. I like to call it highest timestamp wins. What is the underlying principle below that? what we are going to do is for every update that we're going to issue, we are going to add some metadata, some extra information. So when we update locally the object, we're going to retrieve a timestamp, some timing information that should be unique and should also be monotonically growing. And this is the information that we're going to propagate then to the other replicas when we are synchronizing on the update. So what happens in this situation is that the update of x to value 3 is annotated with the timestamp 12. The one up here is annotated with timestamp 45. If I now transmit this update 312 to the first replica, it will check, was the update that is transmitted here earlier than the one I did? If so, then I'm going to forget about it. Yeah? I'm the last writer, I'm going to win. So the value here stays 45. In the situations where this 12 was prior the data state, if the other update here arrives with timestamp 45, I'm going to replace x by 1 because this happened later. Yeah, so also for this replica, we end up here with x being equal to 1 in the end. Yeah? Works with any kind of data. Just look at this highest timestamp. Now, the problem is, where do I get the timestamp from, right? So I'm kind of moving my problem to a different level, because in order to get such a timestamp with these properties, I need to do something like installing a global clock server. So moving my synchronization point to a different position. If I only would use local times here, it's a bit difficult, because if somebody starts doing something with their clocks, right? I'm just going to put my clock forward, so I'm going to win on every write. That's probably not what you want to have. We want to have some form of fairness there also. So we would need to have a global clock server, which is going to be our bottleneck eventually, or we would have needed to have some physical clocks that we could use, but it also needed to be synchronized in a certain way. So yeah, people use that. It kind of works, but it has some issues. Another generic policy is a so-called multi-value register policy. So what do we do there? If we have two different updates that happen concurrently, what I end up with is just I keep both of these updates. Multiple values, that's where the name comes from, multi-value register. I just keep both of these updates. So, and then it also does not matter in which order the updates arrive. I have the set of 1 and 3 here in all cases. Yeah? So both replicas here agree that it should be the set of 1 and 3. Now the problem is, which one is it now, 1 or 3, right? So what you need there is actually, it's not fully automatic in the sense that you would need to have now a party that kind of decides in the end, if I have multiple values here, what should be the real final value. Yeah? So think about our calendar application. If somebody wants to move the date to 9 o'clock, another person wants to move the date to 11 o'clock, well, you can say it's either 9 or 11. You probably have to phone somehow, and one of them is going to say, okay, it should be 9 o'clock, right? So what you usually do there is you escalate this conflict resolution to the user level, which is acceptable and maybe sensible for some applications. So that's kind of the conflict resolution that we know from version control system or workflow systems, right? So version control systems, I'm going to say my update is going to win, not yours. That's in essence exactly this problem. Now, if we look at the data semantics, we can actually be more clever. So instead of saying, if I know, for example, that this integer that I was talking about is in essence a counter where I'm starting to count things, I can be more clever. Instead of saying the new value is 1, what I could say here is I want to actually just increment the value by 1. And instead of sending the new value over, I'm just going to send the operation over. So here incrementing by 1 will set the value of x to 1, incrementing by 3 will set a value of x to 3. If I now forward this increment by 3 to replica 1, the new value could be 4, but just applying both of these updates. And the nice thing is, because this addition is commutative and associative, I end here up with both replicas having the same value, 4. Right? And if this is a counter that's really counting events or something, maybe that's exactly the semantics that you want to have. Might not be all the time the case, right? So if it's really an integer that denotes some value, that's maybe different. But counters occur very, very frequently in distributed applications. So what you need to have in order to provide such a semantics is, in essence, on the database level, for the communication between the replicas, some reliable causal delivery, and you need to make sure that concurrent operations must commute if you send the operations over and apply them. Works very nicely for the counter. Works also very nicely if you have sets. Sets are also a very common data structure. So if you have here a set, so assuming that X is a set, not an integer, you can add 1 to the set. You can add here 3 to the set. In the end, X will just have both values. Adding to sets has also the nice things. Now the problem is, if our operations are not only add, but we also want to be able to remove operations, we have an issue. If I'm adding the same object twice, things should be okay. If I'm removing the same object twice, things should be okay. If I'm adding and adding two different values concurrently, so sorry, these bars here are going to say this is happening on one replica concurrently to this happening on another replica. Yeah, so if on two replicas I'm adding the same value, it should be in the set, everything is fine. If I'm adding two different values, in the end, both of these values be in the set. That's exactly the situation from up there. If I'm removing different values, everything is fine. If I'm adding one value E, and removing another value F, everything is good. But there's one operation that does not commute, namely, if I start adding and removing the same value. So let's look at the execution depicted up here. What happens here? I have here replica 1, where I add 1 to the set. I add 3 to the set. I kind of forward the information to this replica down here. By some weird chance, they're not ending up down here, right? Network is doing something strange. So concurrently to these adds here, I'm having here another replica adding the value 3. Now, the problematic situation is now that this replica, prior to seeing that this is added, is removing 3 here. So in this replica, after adding 1, adding 3, removing 3, the only element here is 1. Now I have this concurrent add. If I'm going to add the value up here, I would have 1 and 3 in the set. If I'm going to follow the operations that are happening here, namely adding 1, adding 3, removing 3, if I remove 3, it should only have the value 1 in the set. Yeah? So things are diverging again, because add and remove do not, adds and removes of the same element do not commute. Yeah. So what I need to come up with now, if I want to design a data type that works with automatic convergence semantics, I actually need to go back to my list of requirements. So I want the this conflict resolution to be deterministic, for sure. I want it to be independent of the order of delivery, so both these situations should yield the same result. It should be also independent of the local state, and it should not require additional extra synchronization. So what could I do? Linearizability, kind of saying I'm going to fix the order in which these operations are happening, is not a way to go, because this will require synchronization. I could use something like this last writer wins approach. So I could either order the add before the remove, or order the remove before the add by using the timestamps or something. This would work, but yeah, comes back to the problem with the clocks. I can add an error state saying something bad happened, kind of similar to this this multi-value approach, saying there is some issue with this value here. But another way of resolving the situation is saying whenever I have an add that has a concurrent remove, the add is supposed to win. Can also be, right? So I'm going to say always the add is going to win, and of course I can also say can also fix it the other way around, saying the remove should always win. Yeah? And these two variants are actually the ones that we consider most sensible. So we have an Antidote DB also a set data type with add win semantics, and we have also one with remove win semantics. And then you can really use this set data type in order to perform your operations as I've shown before. Yes?
Could you also do tombstone as well?
Excuse?
Tombstone, to actually kind of keep track of which have been removed and which have been added, and then
yeah. If you're not careful, well, there's a way of implementing data types like that. Yeah. I'm not talking here about how these things are implemented. There's some machinery happening in the background. So one thing that we, on the database level, need to do is we need to track which operations are actually concurrent. Right. So I'm not going to tell you how this is done. You usually use some form of vector clocks or so. And yeah, you can also use tombstoning in order to do that. If you're not careful, tombstones will accumulate, and that's exactly one of the problems. So yeah. So you might end up with tombstones, but then you at some point need to do some form of garbage collection, of getting rid of them. We have some ways of managing this metadata such that we make sure that this information can be compacted. Yeah. Okay, what are other problems? As I said, last writer wins using local clocks, physical clocks. Clock skew can happen, which is bad. What you also need to prevent is that, or what you also usually need to provide is item potency for this operation-based CDTs, where you're sending the operation and doing it again, because it could happen that the operation reaches you on different paths and so on. So if you really design your own data types, this is something you need to take care of. Metadata, there is some metadata hidden, didn't show that, but if you're not careful there, your metadata easily overgrows your actual values. So you have to be careful there. You usually have version vectors that tell us keep the track of the state on different replicas. The problem is the version vectors typically grow in order of n, where n is the number of replicas. And if you do georeplication to 3 sites, it's okay. To 10 sites, it's maybe okay. It gets an issue if you start replicating things on every mobile phone, right? Then you really run into issues. But we're working here on some ideas also how we can push this idea of always available to the edge, like to mobile devices. CRDTs have a lot of success stories, so a lot of companies are actually using this. These ideas are also ported, meanwhile, to other data stores. But what you don't get with other data stores is what Antidote gives you as support for application invariants. So a little bit running out of time. So just let me sketch a few things. Typically, when you have a data store, you have one way of configuring the consistency semantics for this. Yeah? You can say, I want it to be serializable, I want to have snapshot isolation, I want it to be eventually consistent or something. The problem is, if you look at the range of applications that are out there, this one-size-fits-all consistency model really does not exist. So what you can do, you can either be over-conservative and choose something that gives you more than you actually need, and you're going to pay for that, or you're going to risk anomalies. So this is what we have where we use these very simple key-value stores, and where we have the issue of concurrent modifications, data diverging, and so on. Typically, applications have logical constraints that tell you how the database should behave, what kind of constraints on the data should be enforced. And what we are planning, or what we are working on also, is something that we call just right consistency. You want to make sure that we tailor the consistency choices to your individual application. You give us your application, we are going to look at it and going to tell you this and this and this is the synchronization that is required in order to keep your data consistent, to keep the application invariants consistent. It turns out that there are a few invariants that are AP compatible, so that you can easily maintain on an AP data store such as Antidote, and there are a few that are cap sensitive, which means for these you need to do more synchronization. So for these you need to have special ways of dealing with the situation. The AP compatible invariants are those that work also during asynchronous operations. So these updates can occur locally without blocking, so without requiring communication with other replicas, can be done fast, available, and concurrent. keeping relative order of updates is one of these invariants. So if I, for example, always want to make sure that one value is bigger than the other, and I'm only going to increment them, I have to increment x first, y second, in order to keep this invariant. I need to make sure that my updates arrive in exactly this order. Also, joint updates are AP compatible. If I just send some updates together and apply them in one blob atomically, so this is where our form of transaction comes in, there are other updates that can be, other invariants that can be preserved. And luckily, CRDTs are also an AP compatible data model that helps you to keep some of the invariants. So the consistency level or the consistency notion that Antidote provides is a transactional consistency level, which means that you can make writes observable in an all or nothing manner. So they will be made available to other replicas for reading in one go. And we also make sure that updates converge. So if you only build on CRDTs, on the CRDTs that I've shown you before, so on these replicated data types that I've shown you before, your transactions will never abort. Also very much simplifies the application logic. For the reads, if you read several values within the context of a transaction, you're guaranteed to observe a consistent snapshot. So it's like when you start your transaction, you kind of fix the amount of updates that you're going to see. These will be incorporated in the snapshots. Everything else that happens concurrently will be only made available once you finished with this one transaction and eventually start a new transaction. An essential mechanism that we use in providing these guarantees, and also the guarantees that you kind of see your own writes and other classical database session guarantees, is causality. So causality makes sure that whenever you have different operations happening on different replicas, the order in which the operations are made visible at the other replicas respect the happens before order. So if U happens before V, and V is visible on the replica that you're contacting, U will also be visible. The update U will also be visible. So we're kind of ensuring that these ordering anomalies that you that might happen otherwise, that they're not being observable from the outside. So let me compress this to one more slide. So as I said, there are also invariants that cannot be kept in these available partition tolerant systems. One of these is when you're in a situation where you have a scarce resource. So you use a counter that is bounded by some value. Yeah? For example, the counter could denote here open seats in a cinema. Yeah? So what happens is, as long as there are a lot of seats available, you can easily count up. But if you kind of come down to a few things, the replicas actually should coordinate in order to not oversell. What we have currently today is they will oversell and you will get a phone call and things will be nasty. But what we want to have is we want to ensure on the database level that things don't go bad. So how do you classically implement this? Well, you have some form of reservation mechanism. So you kind of split the available resource into different charts and give reservations for these resources out to the different replicas. As long as you have locally enough of these reservations, you can just execute the operation. You know you're not going to oversell. If you run out of them locally, you're going to contact somebody else and they were going to give you what they have in some way. And this is also an idea that we implemented in a specific data type. So it's a bounded counter replicated data type that requires synchronization only close when reaching the bound. And this all happens under the hood. Yeah? So you don't need to worry about these things at all. When you use your application, you just say, my counter that I'm going to use is a bounded counter with a certain value. And at some point, if you use these bounded counters, these cap-sensitive things within your application, you at some point might get then into trouble, because then you might have transactions that really fail. Yeah? If the resource is simply not available, if you cannot catch a reservation or something like that, then this is a transaction that fails. And there is no way of resolving this conflict in a way, because if I only have one ticket, I cannot sell more than one. Right? So with this overview, I hope I gave you a bit of a hint on how to use Antidote. As I said, it's a result that we came up with in a research project. We have a website, antidoteb.com. You'll find more information there. It's freely available, so if you dare to look at Erlang and very non-typed code, you can find it also on GitHub. The Antidote Haskell client has started. If you're interested in using Antidote and using these techniques, just write consistency in one of your problems, in one of your applications, I would be very happy if you get in contact with me. This work has been done by more than one person. So this bunch of people I'm naming up here are the ones that contributed to the Sync-Free project, which was an EU project that terminated in 2016. We are now taking the ideas that we had for Sync-Free, for synchronization-free programming, to a next project called LightCone, where we look at lightweight computations at the edge. So where we are looking at how we can push the data, push the replicas even further to the network edge on mobile devices, on IoT devices, and things like this. So there will be some more features coming up. Just to recap, to remind you, what you get with AntidoteDB is a cloud-scalable CRDT database. We've been able, in experiments, to scale it to, I think, 5 data centers, each hosting 20 nodes or so. So it shows some scalability. We have high performance, so you can get intra-DC parallelism by sharding. You can have more performance by installing more data centers, such that you get a widely geo-replicated setup. The semantics that you're going to program against is, in essence, transactional causal plus consistency, which means that you get atomic updates. Updates become visible in several updates to several keys become visible within one transaction. The nice thing, so what I had to skip, is this allows also for non-normalized data. What you usually have with AP databases is that you cannot nicely reference other entries. So atomic updates plus some extra mechanisms would allow you to also get referential integrity on your AP database. We have transactions that allow you to operate on a consistent snapshot. The order in which updates become visible makes sure that causality is preserved. And all in all, this helps you to deal with these AP invariants. For the cap-sensitive invariants, as we've seen with the ticket selling application, we provide you with things like bounded counters. We also have plans of integrating strongly consistent transactions, serializable transactions, in addition to these transactional causal plus consistency transactions in the future. It all depends on your application, right? So you have to really look at what you actually need for an application, and then you can be fast and safe. Thank you very much.
Time is mostly up, but we have time for 1 or 2 quick questions, I think. You talked about this bounded. Oh, sorry.
You talked about these bounded counters. In the case for your ticket selling, it's quite easy to see, okay, but you just strip this, you are going to sell 10 tickets, you're going to sell 10 tickets, and it's fine, right? But what, for example, maybe you're talking about user accounts, maybe balances, right? So now everybody has their own balance, and it's not so clear anymore that, it's not so easy to say, okay, this node is going to be responsible for X% of your balance.
Why not?
You can do that as easily?
Sure. I mean, you can. We have a few example applications. One of them is this classical bank account, right, where you transfer money from one account to another account, and well, you can transfer as long as the locally available money on this one replica is going to work, then you can do that, surely.
And then this replica is then responsible for that part of your balance.
Exactly, yeah.
Okay.
Should. So this, in principle, this works, yeah.
There's probably other people who've had the same experience as me of the first time we read Aoife's blog with the Jepsen tests. How well tested is Antidote?
We have not contacted Kyle yet, but it's one of the plans. So it is getting his Antidote Jepsen approved is probably, hopefully, going to happen spring or so. I have to talk to him. But in essence, this has been developed by a large group of people. It has started as an academic project, in essence. We are now transferring it. We are planning to transfer this to an open source community, and we are also are in the process of starting a startup that is going to help people dealing with these problems. Getting highly available partition-tolerant applications. We have a lot of regression tests running in there. We use as much type checking as we can get from Erlang, which is unfortunately not a lot. But you will find some bugs for sure. But what I've seen from other databases that are out there, we are comparable, I guess.
It's just good to know that you're taking it seriously.
We are taking it very seriously. Yeah, we have a CI server. It's run on GitHub. We have also a few people now that are outside from our project that start using Antidote. So within the new EU project, companies like HaskellX, which are well known for building highly available, very resilient layers, are investigating into Antidote. They have built prototypes on top of that. So. If you want to use it in production, you should check with me first. But just that I know, right? So, but yeah, I think it starts to become serious for usage.